Welcome to Mrs. Z's Chemistry. In this video, we are going to learn about titrations. Titration is a lab technique that we use to find the concentration of an acid or a base that we don't know the concentration of. And this involves a solution of known concentration, which we call the titrant, and we slowly add the titrant to the unknown until the reaction is complete. Once the reaction is complete, this is called the end point or the equivalence point. And then we can do some calculations to figure out what the concentration is of the unknown. So here's the setup for the lab technique of titration. We use a burette stand right here. The burette is a piece of glassware that looks kind of like this. We're going to talk about this more, but as you can see, it starts by a 0 at the very top, and it counts backwards until either 50 or 100, however large the burette is. And this is what's going to hold the titrant. At the bottom, we have a flask, the titration flask, and this is where we place the unknown concentration sample in there. It's the solution that needs to be titrated. So let's go ahead and look at a sample problem, and this will explain what's happening in the titration lab. You are titrating 22 milliliters of HCl of an unknown concentration. Let's pause there and look at what's happening. We have placed 22 milliliters of hydrochloric acid into a flask. We have very carefully measured this. This is an exact measurement. We don't know what the concentration is. This might be 1.5 molarity, it might be 0.2 molarity, it could be 3.1 molarity. Who knows what the concentration is? For whatever reason, we don't know the concentration. And this is what we're going to try to figure out. Continuing on with the problem, it says that this unknown concentration is being titrated with a sample of 0.15 molarity NaOH. That is placed in the burette. So we have poured a sample of NaOH that has a molarity of 0.15. So we know the concentration. This is the titrant. It is the known concentration solution. At the beginning, your burette reads 25 or 0.25 milliliters. So again, like I said, the burette counts backwards. So when we have filled up the burette with sodium hydroxide, our meniscus is going to be somewhere at the top here. And you need the meniscus somewhere, just anywhere below the 0 so that we can actually find a marking for it. And we're going to read this and count it backwards. And it says that at the beginning, it was recorded as 0.25 milliliters. This doesn't mean that we have used a quarter milliliter. It doesn't mean that we have a quarter milliliter. We clearly have way more than a quarter milliliter. It just is the beginning marking. And I'll show you how we use this in a moment. So then it says you use 2 drops of phenolphthalein indicator. That's a very big word there, phenolphthalein. But the indicator is, you can kind of think of it like liquid pH paper. It will change color at a different pH. In this case, this phenolphthalein indicator is clear in the presence of an acidic solution. So when we add 2 drops of the phenolphthalein indicator to our acidic solution in the flask, it's not going to change the color. It's still going to be clear. But then the phenolphthalein indicator changes to a pink in the presence of a basic solution. So this is how it works. It says, after carefully titrating for a while, your solution turns a beautiful light pink color. So that means we have turned our little stopper. When it is turned parallel with the glass burette, then our little drops of base start dropping into the solution. And we drop it in, and at first, as soon as you start dropping the base in, we still have a vast majority of the solution is acidic. We have used up all of the base and reacted it, but we still have leftover hydrogen ions in our solution, so it's still clear. As we get closer, you can imagine the meniscus is slowly dropping down the burette, and as we get closer to the end point, meaning the completion of the reaction, the solution starts turning pink. Let's get a pink color. The solution starts turning pink in here as the drops are touching the acid. If you swirl the flask at the bottom, it helps the reaction to react and mix together, and often the solution turns back clear, and that's because all of the base got reacted and it's still an acidic solution. But at some point, all of the hydrogen ions completely react and we don't have any hydrogen ions left. Then the entire solution turns pink. We actually would want a very light pink color. Let's go ahead and use this to see the color. The whole solution turns light pink, and assuming it doesn't turn back to clear, that means you have reacted all of the acid, and we stop. We turn the stopper off. We don't want to drop in any more. Even one more drop could turn the solution even darker pink, and that would mean you've overshot the titration. You want to make sure it is as light of pink color as possible. So that's what this is describing here. After carefully titrating for a while, your solution turns a beautiful light pink color. You stop and read the burette again. It reads 12 milliliters. So in this example, the meniscus dropped all the way down to somewhere around here, and it says it was read as 12 milliliters. Of course, these numbers aren't really to scale. But in the problem, we started out at 0.25 milliliters on the burette, and we ended up at 12. And then it just asks us, what is the concentration of your HCl sample? So the first thing we need to do is figure out the volume of sodium hydroxide that we ended up using. If the meniscus was exactly on the 0 at the beginning and then it ended up at the 12, that would mean we had delivered 12 milliliters. But the meniscus was not at the 0, it was at the 0.25. So it's the difference between the beginning and the ending reading that is the volume of sodium hydroxide that we ended up using. So we take 12 minus 0.25, which means we used 11.75 milliliters. That is, if you look at our molarity equation, molarity is equal to moles per liter. So if you multiply molarity times liters, we get moles. And that's what we want. We want to know how many moles of sodium hydroxide did we use. So here's our molarity. Let's move it over a little bit. And then the volume in liters is 0.01175 because there are 1,000 milliliters in 1 liter. When we multiply these together, we have 0.00176 moles of sodium hydroxide. Now, the key part to this is that the moles of sodium hydroxide equals the moles of hydrochloric acid because they react in a 1-to-1 ratio. So using stoichiometry, we could go like this: 0.00176 moles of NaOH. According to the chemical reaction, we have a 1-to-1 ratio. For every 1 mole of NaOH that reacts, we also need 1 mole of HCl. The HCl was what was in the flask down here. So if we used 0.00176 moles of sodium hydroxide, that means we also originally had 0.0176 moles of HCl. So we know that in the original 22 milliliter sample of hydrochloric acid, we had 0.0176 moles of HCl. We need to find the molarity of the HCl. Molarity, again, is moles divided by liters. So turn this value into liters. Oops, we need another 2 in there. When we multiply or divide these, we get a molarity of 0.080 for hydrochloric acid. And that is the end problem. That's exactly what the problem was asking us for. What is the concentration of the hydrochloric acid sample? And we're talking about the original sample, so we don't add the volumes together because we want, before we titrated, what was the concentration of this unknown sample of hydrochloric acid? And it was 0.08. So let's go ahead and look at this a little bit closer. This is a close-up view of the burette. As you can see, it starts out as 0, and we're counting all the way down. This one goes to 50 at the bottom. So when we need to record the values, we have to remember that they count backwards. So this is if the meniscus was right on this line, that would be exactly 28.00. This line would be the 0.1. This line is 0.2, 0.3, 0.4, 0.5. You can see our meniscus, though, is right here. So there's the 0.5, 6, 7, 8. So we have 28.8 right here, and we're not quite to the 28.9. So we're right in the middle somewhere here. So we could record this as 28 maybe 88, or you could potentially say 28.89 or 28.87, something around there. As you can see, we're not quite to the 28.9 line, and we're in between the 28.88 then. Remember that you always have to estimate one digit between the tick marks. So because the tick marks record to the 10th place of the milliliter, that's why we need our estimate digit is the 100th place value. So any of those values would be appropriate. Even 28.85 would be fine if you want to say the meniscus is right exactly between those two numbers. All right, so let's look at this sample problem. This is more of a vocabulary problem here, and just remembering what the different words mean. If you have 20 milliliters of hydrochloric acid of an unknown concentration, and you perform a titration experiment using 0.14 molarity sodium hydroxide, which one are you titrating and which one is the titrant? So if you go back and look at the original problem, the way it was worded, as well as the original slide, right here, the solution of known concentration is called the titrant. And the solution that is the unknown is the one that we are titrating. So let's look at that problem again here. Which one are you titrating? That would be the hydrochloric acid is the one that we are titrating. And the titrant is the sodium hydroxide where we know the concentration of it. It's important to be aware of these vocabulary words, otherwise the problems can get really confusing if you don't know what the words mean. So let's go back to the mixing acid and base type of problem, because these problems sometimes get a little bit mixed up and easy to confuse them. In the titration problems that we were just doing, we're trying to neutralize the reaction. So the moles of the acid equals moles of the base. And once you find the moles of one of them, then you can find the moles of the other. But in a mixing acid and base, while it does still react 1-to-1, we want to subtract the amount of moles we have of each, because we know both the volume and the molarity of the acid and the volume and the molarity of the base. So when we find the moles of each of these, then we can find how much is left over of one of them. And then we have to add the volumes because we've added both of them, and we want to find the pH after the solution has been mixed. Whereas in the titration problems, we're not trying to find the concentration after the two have been mixed. We don't really care about that anymore. We know the pH would be probably 7. It should be very close to 7 because it's been neutralized. What we're trying to find in the titration problems is what the concentration of the acid is before you do any reaction. So let's go ahead and solve this problem. We need to find the moles of each. Let's go ahead and color code this red for acid. When we take our 0.750 liters, that's milliliters turned into liters, multiply it by 1.3 molarity, this is for the acid, we get 0.975 moles of hydrogen ions. Remember, we really only care about the hydrogen from the acid. Then we take our 0.650 liters, multiply it by 1.3 molarity. For the base, I should be doing this in blue. We will get 0.845 moles of hydroxide. Then, when we mix these two together, one of them is going to run out. And you can see that the hydroxide, we have a lower value. So that's the one that's going to run out first. And we're going to have only 0.130 moles of hydrogen ions left over. In order to find the pH, we need molarity of the hydrogen ions, not just moles. Molarity, of course, is moles divided by liters. Now imagine we have poured 750 milliliters into a beaker with 650 milliliters. So now that is 1,400 milliliters, and we need to convert that into liters. So our molarity equation is 0.130 moles of hydrogen ions divided by the total value or total volume, which is 1.4 liters. And so then our molarity is 0.0929. And this is the hydrogen ions. When we take the negative log of 0.0929, that gets us pH, which is 1.03. And then double check, does this pH make sense for this situation? Well, yes, because we know that we had hydrogen ions left over in the solution after we mixed these two. Therefore, this is an acidic solution. So the pH should be anything less than 7